about quantum theory of measurement based more or less on what was really formally explained for the first time in the textbook, in the book by von Neumann on quantum mechanics, where basically all the elements which will be at play in this lecture are very properly set up. Of course, von Neumann did not invent all that, and you see on the right all the founding fathers of the quantum theory who formulated the postulates as you learned it in introductory course about quantum theory. But von Neumann really put this clearly in this book, among many other things, about quantum theory. And so I will focus on what is proposed in the chapter 6 of this book, which is about the measuring process in quantum theory. So I will not, of course, present all what is in this chapter, but just focus on this picture, which is kind of a short view of the vision of von Neumann about, and of founding father of quantum theory about the measurement, that he imagined a process like a complicated chain linking the microscopic system for which the laws of quantum mechanics hold. So you have a wave function or state vector to describe the system. You have a superposition states, quantum interference, entanglement. And then you have a measurement apparatus. And then he considers that this was not enough because you can put everything in a big quantum superposition. So he increased the size of the system as much as he can to complete all the list of elements involved in a measurement process. So in this chain, one introduced the photons that are used to look at the system with the microscope, if the system you use to observe is a microscope. Then the photon hits the retina. Then the retina excites your neurons in your brain. And in the end, a kind of provocative question consists in saying, okay, you eventually are also embedded in this chain, and is there a role of consciousness in the way the measurement proceeds? Is it a solution to the so-called measurement process to imagine that it's when you think about the result or you make aware of the result that projection postulates arise? So it's not at all what I want to say, but that was the illustration of what von Neumann had in mind when he imagined a measurement chain from the microscopic to the most complex object, which is the experimentalist looking at the apparatus. And indeed, I think it's kind of anecdotic to make consciousness play a role in this case. Which is less anecdotic is to set the questions, which is where does the concept of superposition state of vector stops? And this is related to the problem of the Schrödinger cat that I will discuss in the last lecture. But for today, I will focus on exploring this problem with the point of view of what can be done in cavity QED experiment. And I will focus on the first part of what is the measurement theory, where we will put simple things as simple as possible. So I will just accept the projection postulate and try to make it work in a real experiment. So in order to introduce the experiment, indeed, I would like to insist on some very basic properties of what is called an ideal quantum measurement. And I think it's important because it's the thing you are taught in the first classes of quantum mechanics. Then I guess you find it very strange. And then when you look at real measurement apparatus in the lab, basically none of them corresponds to this postulate. So it's kind of very strange that these postulates, which looks like not corresponding to the way measurement apparatus are built, are still efficient to predict the result of experiments. And so I think one of the goals here is to explain why it works, even if it's an oversimplification of the real world. And for that, we'll use a model situation with the minimal possible element to describe the measurement process by using Rydberg atom and cavity QED. So just reminder of the measurement postulates. So I like very much to put as the first step of the postulates the fact that quantum theory is a statistical theory. It does not predict a result for sure, except in very special case, but intrinsically, quantum theory is a theory of random events, and these random events as the results of measurement. And then we can start to introduce the mathematical formalism for this intrinsically random theory. So the quantity you are allowed to measure are then introduced very mathematically and formally by saying that a measurement corresponds to some Hermitian operator. So the first time I heard that, I think, okay, it's nice, but how does it look like with respect to measurement apparatus? It's related, but kind of indirect. And then, once you accept Hermitian operator, you have to accept another thing, which is eventually even stronger, which is the projection postulates, which can give the feeling that when you look at something, you change the thing just by looking at it, and that something strange appear in a measurement, which could eventually, if you push the thing to the limit as Feynman, you could eventually imagine that your consciousness is responsible of projection postulates. Indeed, I think we don't like physical theory, which depends on when you think with your brain, so I try to have a more objective representation of what a quantum measurement here. So here is a simplified version of the Feynman chain, a single quantum system represented by a single atom related to some apparatus. Then the measurement results have some real value named A, which are related to some Hermitian operator A hat. So this is a simple postulate, 3 points. And indeed, it's very efficient, because once you learn that, you can predict the result of experiment performed on quantum system. You can solve problems mathematically and get the proper probabilities, but it does not tell you at all how to build an apparatus which actually performs this strange kind of thing. And my goal today is to construct an apparatus and look at the very detail so that you understand how a real apparatus finally works like this and respects this very simplified and very easy to apply postulates. So I mentioned here again some of the shocking consequences or counterintuitive consequence of these postulates. Indeed, it seems that quantum theory combines Hamiltonian evolution and discontinuous events called projection, responsible, if you push the logic, to the existence of quantum jumps. So it's very strange that a theory may coexist two so different evolution, one Hamiltonian, that we like because we are used to do classical mechanics where you have some Hamiltonian or you have some force, then you write the Newton equation and everything is determined and the story is finished. Here, it seems that we put at hand one other layer of kind of evolution, which is what occurs during the measurement, which looks mysterious. Why should not Hamiltonian evolution apply, even including the measurement apparatus? And indeed, this is, of course, related to the Schrödinger cat problem that will be discussed in more detail in the next lecture. So I will come back to this problem later. But before going into the experimental construction of this measurement apparatus, I would like also to present you how the founding fathers of quantum theory imagined such a strange postulate, because they did not, of course, imagine this from the scratch, saying, okay, it would be nice if in the theory we have projection and that. No, they start, of course, with observation. And the observation driving the founding fathers to this projection postulate is the observation of disintegration of a particle using the Wilson cloud chamber. So in this cloud chamber, when a radioactive particle emits some other particle due to radioactivity, then you see trajectories appearing as a signature of the emission of this particle resulting from radioactive decay. So what is strange in that, and what is pushing in the direction of the projection postulate? Indeed, if you want to understand that, you come back, as very often when you want to understand quantum theory, to a dialogue between Einstein and Bohr, with Einstein coming with a very clever question and Bohr with a very clever answer. And so the question here is formulated by Bohr at the Solvay conference in 1927. Mr. Einstein has considered the following problem. A radioactive sample emits alpha particles in all directions. These are made visible by the method of the Wilson cloud chamber. Now, if one associates a spherical wave with each emission process, which is natural, emission is isotropic, how can one understand that the track of each alpha particle appears as a very nearly straight line? So that was the question set by Einstein. And the answer of Bohr is, as soon as such ionization is shown by the appearance of cloud droplets, in order to describe what happens afterwards, one must reduce the wave packet. So he said, we believe in, we have the projection postulate to explain that. And indeed, we can reverse the argument. In some sense, the projection postulate was invented to explain that. So one must reduce the wave packet in the immediate vicinity of the drops. One thus obtains a wave packet in the form of a ray, because the spherical wave is projected at a position, and as the particle has some momentum, it continues in the direction of propagation, a form of the ray which corresponds to the corpuscular character of the phenomenon. So you see that this discussion was already set at the very beginning of quantum theory, and here is the first step of the discussion telling how quantum objects becomes classical trajectories, even if particles are waves. So indeed, the people continue to think about that, and the next step was performed by Mott in 1929, which pushed the analysis further and showed formally that a particle submitted to repeated observation follows the classical trajectory. So if you take the Schrödinger equation and apply repeated measurement, the average position and momentum of particle follow the result expected from classical mechanics, which is a very satisfactory result, and which tells you that to connect the quantum and the classical world, the observation, or maybe not the observation, but the environment of the particle, when the particles are flying, they are not submitted to abstract measurement. They collide and have interaction with some other atoms, and these interactions, on average, produce the materialization of the wave in the form of classical trajectories. So that's, I think, very interesting result. And indeed, this paper by Mott can be seen as the first recognition of the role of the environment-induced decoherence in the emergence of classical trajectory. Of course, this terminology of decoherence was not used by Mott, but I think the idea is already there. And when we consider environment-induced decoherence, this is looking at this kind of effect that was discussed here. So then Schrödinger also considered that and had a very interesting sentence because he realized that the consequence of observation of wave packet reduction is even stronger if you apply it to discrete variable as compared to the continuous variable, which are the position and momentum of a moving particle. And he says that, okay, if you apply a projection postulate to discrete variable, you expect discontinuity in the evolution of the system. You expect what is called quantum jumps. And then he finds it very tricky. He writes a paper about this in 1952, where the title was the question, are there quantum jumps? And the conclusion of the paper was, no, there cannot be quantum jumps. So you will see that Schrödinger was indeed wrong. But he said in relation to this, in the first place, it is fair to state that we are not experimenting with a single particle any more than we can raise Ictodiorio in the zoo. We are scrutinizing records of events long after they have happened. So here he eliminated the possibility of ridiculous physical effect as quantum jump, not in the same way as in the first sentence I showed in the first slide, where basically he just said one will never experiment with a single particle. Here it's a bit more a subtle argument. He said, okay, even if we measure, we always look at the system very long after. And so the jump will never be resolved because afterwards it's completely finished when you would observe it. And so that was the argument to eliminate the possibility of quantum jumps. So indeed, the argument of post-mortem analysis will just disappear when we consider modern experiments in quantum optics, where we can perform measurement well before dissipation is appearing, which means that we can look more or less in real time at the evolution of a Hamiltonian system under repeated quantum measurement, and then we observe that effectively quantum jump exists, and indeed we'll look at this with the experiment. So then Schrödinger also introduced the Schrödinger cat as another ridiculous consequence of quantum theory, but I will say more details about this in the next lecture. So now I present you a real measurement apparatus whose action is to perform detection of photons stored in the cavity just according to the postulate. So just by perturbing the system no more than the projection postulate. And then that's what is called a non-destructive or a quantum non-demolition measurement of the number of photons in the cavity that we can perform in the experiment. So to do this, I make a jump. Basically, the experiment, the first experiment on the resonant strong coupling regime between atom and cavity was performed in 1996. And then we had hard work to improve the quality of the mirrors of the cavity. And in 2006, we got this exceptional cavity with a lifetime of a photon of about 0.1 photon with a quality factor of 5 × 10, which was indeed necessary to do everything I will explain today. So without this cavity, we would not have been able to perform this work. And indeed, this work, the idea of this work was even before the experimental start. Indeed, what I will present today is a realization of a proposal we did together with Jean-Michel Raymond, Serge, Valérie Lefebvre, and Nissim Zagueri, who was a Brazilian researcher from Rio de Janeiro. So we proposed the method in 1990, and in the conclusion of the abstract, we claimed that with realistic Rydberg atom cavity system, small photon number states down to n = 0 could be prepared and continuously monitored. So we were optimistic. We say with realistic. So it was anticipating about what a realistic was or not. There was kind of risk taken when we started to build the experiment, but it is an example where it's maybe worth to take risks in science. And you see, by looking at this time scale, that when you take risk and start a risky or complicated experiment, the time scale of contracts you get to finance your research does not fit at all with this kind of time scale, which runs over like 16 years for this project. And so we have to find a way to go around that. It was easier at that time. It's more and more difficult, I think, to work on such long-term time scale on fundamental project. So what is the game changer between these cavities and that? Indeed, it's the way we fabricate the mirror. Basically, we started with bulk niobium, so massive niobium, machined with standard machining technique, then polished by optical polishing technique, which makes them, as I answered to questions this morning, it makes them a nice mirror, but bad superconductor. And then the problem starts, because to recover a good superconductor with a polished mirror, you have to etch it chemically. You can try to do electro-polishing, but it's not real polishing. And in the end, you have peaks and valleys with defects size of the order of the micrometer, which limit the quality factor here to like 2^10⁸. And for going there, indeed, we changed completely the technology. Instead of machining bulk niobium, we just ask to manufacturers, which are experts in fabricating mirrors, to machine copper mirror for us. And the copper mirror is machined with a technique where this toroidal surface is machined with a roughness less than 10 nanometer, and with a very regular surface without ondulation. So this very good copper mirror has a good geometry, so that diffusion on the mirror roughness is negligible for up to quality factor of the order of 10^11. And then by a sputtering technique, so it's a magneton discharge which induces a plasma, which ionize an niobium atom, which are deposited on the copper mirror, you can have a layer of niobium over copper of about 5 micrometers thickness and still have a very good mirror. And the sputtered niobium is you do the proper cooking, and we had the help of CEA in Saclay in order to do this. If you have the right machine, you have very nice niobium with very high conductivity in the microwave domain, and that's the way we achieved the highest quality factor we get for the experiment, which corresponds to 4^10⁻10 in terms of quality factor. It's 4 billion bounces back and forth of the photons between the two mirrors. And to make the thing more intuitive, it corresponds to a tenth of a second lifetime of photon in cavity, and 1/10 of the second is the time you need if you have a photon flying at the velocity of light, and which makes one full round trip around the Earth. So you can imagine that the distance run by the photon between the two mirrors is one round trip all around the Earth in a mirror, in a cavity with a separation between the two mirrors of only 3 centimeters. So that's the kind of cavity we achieved to realize. And so it's a very good photon box, isolating very much the cavity field from the outside environment over time scales which are orders of magnitude longer as compared to the interaction time with the Rydberg atom, which is tens to hundreds of microseconds, and which is also a time scale which is infinity of the scale of the atomic lifetime in the range of tens of milliseconds. So then, the new setup, you have a picture of the new setup. So it does not tell you much. It's a bit more professional as compared to the first one. And you have several blocks, which are the one after the other. So the cavity is this box. Indeed, there is a second similar cavity, because in this setup, we can afford to have 2 cavities. And in the last step of the experiment, we perform 2 cavity experiments. And then you have 3 other boxes around the cavities, which are low quality factor cavity in order to prepare quantum superposition states of the atom and to probe them before detecting the atom. Then you have a box which is covered with some material which shrinks the magnetic field and magnetic field fluctuation so that we have a good coherence time for the atomic superposition in the experiment. So inside the box, the cavity block looks like this. You have one mirror. The top mirror was removed. You have electrode around to screen all the environment and to have a good control of the electric field seen to the atom to avoid field gradients, which would spoil the atomic coherence. You have piezoelectric stack to make the fine-tuning of the cavity resonance on the atomic resonance. And then, when you put everything together, here is the symbolic representation, a schematic representation of the setup, which looks very much like the first one, with an atomic beam. It's again a fast atomic beam, thermal atomic beam. Typically, we use atom crossing the cavity at 250 meters per second. The gray box is the place where circularization of the atoms occurs. And then you have the high Q superconducting cavity, so the photon box at the center of the setup. And on both sides, you have the low Q cavity I already mentioned on the picture, which basically allow one to control the geometry of the spatial geometry of modes of microwave, which are driven by a classical source. This is a classical source, a microwave synthesizer, radiating microwave at 50 gigahertz. And then in this region, the atoms are submitted to the interaction with this microwave, and they perform a pi/2 pulse in a classical field. And in the second low Q cavity region, again, they are submitted to a pi/2 pulse. And those of you who know about clock, atomic clock technology, indeed, this is nothing else than a clock setup. It is the Ramsey interferometer setup, in which one starts to induce an interaction with the atom. Then one prepares quantum superposition, which evolves freely at the clock rate set by the atomic spectrum. And in the end, we probe the state of the atomic clock by comparing it again with the synthesizer when performing a second pi/2 pulse. So this is a Ramsey setup for really fabricating an atomic clock. And then the principle of the quantum measurement consists in looking, using the way the presence of photon in the cavity will affect the rate, the ticking rate of the atomic clock. And then, after interaction with these various cavities, the atoms are again detected one by one. And for each atom, we get a binary answer, which is atom in E or G. And in terms of fictitious spin, E will be represented by spin up and G by a spin down state. So what is the principle of the clock? The principle consists in having a quantum superposition of E and G, which evolve at the energy difference between E and G. And then when the atoms are crossing the cavity, they experience in this experiment a non-resonant interaction with the cavity. Why do we want to have non-resonant interaction? We want to detect the photon without changing, without absorbing them. That's the principle of quantum non-demolition. If you want to have a projective measurement, we should not absorb the photon, as does usual photodetector. So we set the interaction to the non-resonant regime so that Rabi oscillation does not occur. And if you look at the 2x2 matrix representing the non-resonant interaction, it's easily diagonalizable. And you find here is the result of perturbative calculation to second order in coupling. You expect a light shift induced by the photon number stored in the cavity, proportional to the square of the vacuum Rabi frequency divided by the detuning. So that's a usual result of second order perturbation theory. So the lower state J is also affected by the coupling with the cavity, with the difference that for G, just the light shift is proportional to n, whereas it's proportional to n plus 1 for the excited state. The one term here can be seen as the modification of the lamp shift of the atom due to coupling with the vacuum modified by the presence of the cavity. And then we use the atom as a clock for counting the photon number by looking at the accumulated phase shift induced by this light shift on the atomic clock. And indeed, all the difficulty of the experiment is to be able to read out the state of the atomic clock before the photon decay in the cavity. And even if 1/10 of a second is a long time, it's not a long time for clock if you are thinking in terms of metrology. When you make a very precise atomic clock, you have time, so you average for a long time to have a very well-defined, very well definition of time. We cannot average more than a fraction of a second. So the clock has to be fast enough to resolve this light shift in a limited time scale. And indeed, that's what we do. And here is the principle of the first experiment we performed for detecting whether the cavity was containing 0 or 1 photon after the measurement. So basically, we first apply, as I told you, in the first Ramsey region, a pi/2 pulse to the atom. Pi/2 pulse means that we perform, this is the Bloch sphere representing the atomic state. E corresponds to the spin-up state, which sits on the north pole of the Bloch sphere, and G will correspond to the down state of the spin sitting at the south pole of the Bloch sphere. So interaction with the classical field is always like a rotation. This field is resonant, so the rotation is performed here around the x-axis, and if you properly adjust the interaction time, you perform a pi/2 pulse, rotating the spin initially in upstate pointing in the z direction to a spin pointing in the y direction. And the state is represented here. It's the state E minus IG with a normalization factor, which is not plus x, but plus y, sorry. So in terms of spin 1/2, you have a rotation around the Bloch sphere. Then we consider the interaction with the field stored in the cavity containing either 0 or 1 photon. And in the proper rotating frame, when the cavity contains 0 photon, the spin does not move, and it's permanently pointing in the plus y direction. On the other hand, if the cavity contains 1 photons, then there is another additional term in the light shift, which means that in the rotating frame, which is fixed, you will accumulate a relative phase shift with respect to the blue arrow. And if you properly adjust the interaction time with the cavity, the accumulated phase shift for the pseudospin equals a pi. And for such an interaction time, when the cavity contains 1 photon, then the pseudospin points in the -1 y direction. And you see that these two spin states are orthogonal, which means that you create in this non-resonant interaction some correlation between the number of photons in the cavity and the direction in which the pseudospin carried by the atom is pointing. And this correlation, you expect them to be perfect as the two spin states are orthogonal. Indeed, you do more than that. You prepare an entangled state between the number of photons and the spin state that, that will be processed by the next step of the measurement. So that's here the final state of interaction. In the general case, is the phase shift induced by a photon is phi and not pi. You rotate by an angle phi, and you end up, if the cavity contains 1 photon, to the plus state in the direction phi. So then we want to read out the state which is prepared here. If you just measure the atom at this level, you learn nothing about the field, because the measurement perform a measurement of atomic population in E or G, which correspond to a spin measurement along the z-axis. So if you project plus y or minus y on the z-axis, you have the same probability to have G and E, and you cannot discriminate between 0 and 1. So it's not the proper way to measure this system. And then the trick consists in using the second interaction with the same classical field to perform a second pi over 2 rotation, which maps the y-axis over the z-axis. This rotation flips the minus y state into E and the plus y state into G. And now if you measure in the EG basis, you expect to project the field either on the state containing 0 or on the state containing 1 photon. And you see that the first step of a quantum measurement is some Hamiltonian interaction between the two systems. So it's not a mysterious projecting thing. It's interaction, which creates correlation, and which indeed creates more than correlation, it creates entanglement. And then, once you have this entanglement, you will measure one part of the system, and that's the trick, to perform an indirect measurement of the cavity field by using the atoms. Once the atoms, after being entangled, goes out of the cavity, and when you measure the atom, you do not interact with the cavity field, and you expect that the cavity field is still there after the atomic measurement. So that's what we did in the experiment, and from this state, we expect that whenever atom is detected in upper state E, the field is projected on the 1 photon, whereas when the atom is detected in G, the field is projected on the 0 photon state. So now you will see the result of the experiment. So the experiment, which run over time scale, oh, okay, sorry, it started too fast. So here the horizontal axis is seconds, so it's it's much more longer than the cavity decay time. It's like 20 times the cavity decay times. And then during these 2 seconds, we send successively a very weak pulse of atoms repair and Rydberg level, so that on average for each atomic pulse there is either 0 or 1 atom, to prevent the atom to interact by pair with the field, which will make the interaction more complex and which reduce the efficiency of the measurement. So you imagine this stream of atoms crossing the cavity one by one, and for each atom you get a click, either in E channel or in G channel. And you see that initially most of the atoms, about 90% of the atoms, are detected in G. And the fact that some of the atoms are detected in E is not that you have some photon which appears for a very, very short time. It's just the imperfection of the Ramsey interferometer. It's just the fact that the Ramsey fringes have not 100% visibility, and due to some imperfection in the homogeneity in the field, a 10% fraction of the atom does not work properly and are detected in the wrong level. But if you make a majority vote over 3 atoms, you, without ambiguity, you have no ambiguity on the measurement result, and this tells you that during that time, the cavity was empty, because G atoms corresponds to empty cavity. And then look at the evolution as a function of time. And it's like this. So for like 1 second, the cavity remains empty. And after 1 second, something happened. And most of the atoms, 90% of the atoms now, are in the opposite state, in the upper state. And after half a second, indeed, there is a reciprocal change. And again, most of the atoms are detected in G. And here, you can see directly a signal, which is the signature of the spontaneous emission, apparition of a photon in the cavity, which appeared at that time, after a bit more than 1 second, which lasts for 500 milliseconds in the cavity, which is about 5 cavity lifetime, and then disappears suddenly. And you see, these 2 things correspond to the observation of quantum jump of a field jumping between vacuum and 1 photon state. So then you can ask, where does this photon come from? So it's written there. It's black body radiation. So the cavity is not at 0 temperature. In this experiment, it's at 0.8 Kelvin. And then the average black body photon number is 0.05. And indeed, there is a small probability that a black body photon appears in the cavity. It remains there on average for a duration which is on average the cavity lifetime, so 100 milliseconds. Indeed, this photon was very lucky. It has its lifetime 5 times the average. It's not forbidden by quantum theory. Indeed, this trajectory is the longest lived photon we observed in the experiment. So that's why we prefer it, and we show it. And we even give it the name of Mathusalem. So this is the first observation in our experiment of the quantum jump leading to the birth, the life, and the death of a single photon in the cavity. Of course, this is nice, but it's a bit frustrating to imagine that we have a nice system which is harmonic oscillator with infinite scale of energy level, and that we can only probe the 2 first levels of the system. Indeed, formally, when we perform this measurement, we do not discriminate between 0 and 1 photon. We discriminate between even and odd photon number state. Because if you go to 2 photons, as the light shifts are proportional to intensity, you double the light shift with respect to 1 photon. And if 1 photon induces a pi phase shift, 2 photons induce 2 pi and are not distinguishable from 0. And the same argument holds for all odd photon, even photon numbers. And for all even photon numbers, I will give the same signal as the 1 photon state in the cavity. So this is already a measurement of the full extended energy level of the cavity field, but we only get 1 bit of information per atom, which is logical, which is the parity of the field. But indeed, we can do more. And we can generalize the process to count a larger photon number and to discriminate not only between even and odd, but to count from, in the experiment, 0 to 7 photons in the cavity, and even more in a more recent version of the experiment. So how does it work for seeing more photons? Basically, it's the same experiment, except that now, after preparing the superposition state of the atom, we use a different phase shift per photon. Basically, we increase the detuning to reduce the phase shift induced by a single photon. So it's always easier to make the coupling weaker by having a larger detuning. So we do this, and then in the evolution, all the spin states characteristic of the atomic state will spread over the equator of the blocked sphere, and indeed, the effective spin representing the atom can point, in this case, in 8 different directions depending on the photon number, because I choose a phase shift per photon of pi over 4. So you see that this state contains information about all photon numbers. Of course, it's not unambiguous information, because all these 8 states are not orthogonal. Of course, we are sitting in a Hilbert space of dimension 2. So there are too many states to be orthogonal, but still they carry some information, and there are correlations between the direction of the spin of individual atoms and the number of photons inside the cavity. And now we have to find a way to read out this correlation efficiently, and we do it more or less in the same way as in the case of the phase shift of pi. We apply a second pi over 2 pulse, which performs a rotation of the spin state around an axis, which is not anymore the x-axis. If you look at there, we can choose the axis of rotation by setting properly the phase of the second pi over 2 pulse. If you choose the phase of a microwave pulse on the block sphere, you choose the direction around which you perform the rotation. So here, let's assume that we perform the rotation around this axis, which maps the yellow arrow along the vertical direction and the purple one about the down vertical direction. And now we do as before, we detect the atom either in E or G, and this is formally equivalent to a measurement of sigma phi along this axis before this pi over 2 pulse. And then what do we get? Indeed, we get correlations between atom and field. as I told you, these correlations are not enough to detect the field with a single atom, which gives only one bit of information. And indeed, what we do now is to accumulate information by detecting not a single atom, but many atoms. And the cavity is good enough so that the field does not decay during the process of interaction with many atoms, which will allow us to accumulate information about the photon number. So more precisely, here I write the state you get when you make a single atom interact with the n photon state, the n photon number state. And I assume that the cavity is not in a pure state, but in a superposition state of n states with a probability amplitude Cn. So on the picture I presented here, before the second pi/2 pulse, you have the plus n phi 0 is the plus state of the spin along the different n phi 0 direction of the equator of the Bloch sphere. Now let's assume that we repeat the same with n atom. So every atom interacts with the same field, and indeed the collection of atoms gets all with the same correlation with the photon number. But now you have a state which factors out with a number state n, which is the plus state tensor produced n times for the n atoms. And then, if you look at the scalar products between two such states with n atoms, the scalar products is the scalar products between the plus state along n phi 0 direction, the other n prime phi 0. This is smaller than 1 if n is different of n prime. And if you put a number which is smaller than 1 to the power n, it becomes very fast equal to 0. And so, also, single atom states are not orthogonal. If I put many atoms, they become nearly orthogonal as soon as n is large enough. And large enough in the experiment means a few tens of atoms. So it means that if not a single atom, but a collection of atoms interacts with the field, this collection is already kind of a needle pointing out a single photon number stored in the cavity. By the way, here, the state prepared is already a kind of Schrödinger cat, where the mesoscopic system is a collection of n atoms, and the microscopic system is a cavity field. So now, how to characterize experimentally this n-atom state? Indeed, we perform a kind of tomography of this small ensemble of atoms by measuring the average value of the spin along x and y direction. So we basically measure half of the atom along the y-axis by performing a rotation aligning y over z. The other half of the atom, we perform rotation aligning x over z. And we repeat this for a few tens of atoms. And we get number of atoms detected in up-down in each case. And this gives you two numbers, average value of Sx for a given collection of atoms and average value of Sy. And then you know that the spin, which is there, is pointing around this point with some quantum uncertainties, which corresponds to the shot noise of this kind of measurement. And the point is that the uncertainty in the spin direction scales as 1 over the square root of number of atoms you detect, which means that if you detect a large enough number of atoms, the 1 over square root of n becomes, the uncertainty here, becomes smaller than the difference between the two directions, phi 0, and then your collection of atoms resolves the different spin state in the experiment. So that's what we did in the real experiment. So for each preparation of the field, and I tell you later about which kind of field we prepare, we send a collection of 110 atoms. For half of them, we measure sigma x. For half of them, we measure sigma y. And we put a point in the Sx xy plane, where here you have the two numbers corresponding to the measurement result. And indeed, for the first measurement performed in the collection of possible errors, the result was very close to the error, to the spin value corresponding to 4 photons in the cavity. So here we expect from the atomic measurement that the cavity contains 4 photons. And then if we resume this for a lot of collection of 110 atoms, you have the histogram of the average result of the spin measurements. And you see that the measurement results have some randomness, but not point in completely random direction. There are privileged directions corresponding to discrete photon number. So this direction was correlated to field corresponding to 0 photon. And then you can number the peak by the photon number. 1, 2, 3, 4, 5, up to 6 photon peaks can be resolved here. And here, the field measured was a small coherent field, already introduced in the first lecture, with about 2-3 photons on average in the cavity. And you see here on this picture a kind of direct manifestation of the quantization of the field, the field energy in the cavity. I have constructed an apparatus, an atomic clock, which is sensitive to the intensity of the field in the cavity. And without assumption, I discover that the intensities are discretized. And of course, I do not discover anything because we know that photon number is discrete. But this experiment directly demonstrates that, I would say, visually. And the other interesting property of this is that the set of 110 atoms is already a macroscopic enough system to be considered as a classical needle pointing on the photon number in the cavity. So you see the measurement apparatus is constituted by the interaction between the cavity field and not a single atom, but a bit more complex, but not so complex system, which is 110 collection of atoms. And these 110 atoms are enough so that if you accumulate information about all these 110 measurement results, you know without ambiguity where is sitting the atomic pseudospin, telling you here that it's very close to the 4-photon state, and most probably you have 4 photons in the cavity. The interesting thing is that the readout of the clock is fast enough so that the photon number does not change during the measurement. And this can be shown by repeating this measurement successively, not sending only 100 atoms, but 200, 300, and more. And then you see that as a function of time, you have repeated measurements, which become independent every time you have 100 hundreds of new atoms interacting in the cavity, just all repeating that the field is n equal 4 in the cavity and that it did not change during the measurement. But at some point, you see a kind of random trajectory jumping from here to here. And then for some time, the needle is pointing to the n equal 3 photon number. And then after another quantum jump, you observe 2 photons in the cavity, then 1 photon, and then vacuum. And that's really directly observing a sample of 100 atoms. I think the observation of a needle of a meter jumping from different measurement result to different measurement result, which tells you that there are quantum jumps and that you can observe them in this experiment. Indeed, you can make a more quantitative analysis. I will discuss this just afterward of this. You can rigorously deduce the photon number distribution, the probability distribution number, knowing the measurement result of the atoms. And then I represent here the average photon number deduced from the atomic measurement as a function of time. And you clearly see 2 kinds of evolution. There are steps during which the photon number is unchanged, and there are abrupt jumps, not infinitely fast, but we can comment this later, from 4 to 3 to 1 and vacuum in the cavity. So that's observation of quantum jumps. Quantum jumps exist. Of course, we were not the first one to observe quantum jumps. Ions, single ions observed, the fluorescence observation of single ions already demonstrated well before the existence of quantum jumps. So this was not the fundamental issue here. So how do we formalize the description of the system? Indeed, we make a step-by-step calculation of the way the photon number distribution represented by this P of n as a function of number of detected atoms. And basically, what we do is to apply the projection postulate atom by atom once the atom was entangled with the field. And once the atom is entangled, we have the entanglement represented by the correlation between number of photons and direction in which the atomic pseudospin points. And then what we do in the experiment is to set randomly the measurement direction along the 8 possible directions here. And for each measurement direction, let's assume that this, the first atom was measured along X, we apply the measurement postulate to the state vector of the system, from which we deduce the probability distribution of the photon number, knowing the measurement result for the first atom. And indeed, as usual, the full quantum calculation gives you a kind of nearly intuitive result, which correspond to the so-called Bayes law of linking conditional probabilities. So the probability to have n photon knowing this measurement result is the initial probability to have n photon times the inverse probability, conditional probability, the probability to have the state plus or 1, knowing that there is n photon in the cavity. And this have a simple expression. Indeed, this probability is a projection of the phi n corresponding to n photon in the cavity, the spin state corresponding this, on the measurement direction. So you have numbers here, which corresponds, so that these numbers, which correspond to a sine function. The projection of the plus n state on the plus phi state is just a sine function. So it means that after detecting one atom, the initial photon number, here I assume that it was a flat, here it's the initial one is the purple distribution. I assume no a priori knowledge over the field, except that it is bounded at 7. And then, with this flat initial photon number distribution, if I detect the first atom in E, I favor the spin state, the number state whose spin point in the direction corresponding to detecting the atom in E, and I get a new photon distribution, which is a sign, because it's a produce of the purple function by the blue sign here. On the other hand, if I detect G, I use the red sign, which is just in opposite phase. And of course, I favor the photon number which were not compatible with the result A. And then that's one step. And then I resume with a lot of atoms. And the trick is that for every atom, I change the phase of the measurement, which amounts to shift the phase of the sine function here. So that here I am sensitive, I am very well discriminating between 4 and 0 or 7 photon, but there is a big ambiguity between 1 and 7. You see they are affected exactly in the same way. But for the next measurement, the phase will be set at another position, and I will accumulate information about the different photon number. And here is the result of the product of all these sine functions, which indeed are set by the measurement result. And you see that the initially flat photon number distribution progressively evolves with a single peak distribution. Here, a field containing exactly 5 photons. And indeed, what you get from the experiment is a list of cliques, 0 and 1 corresponding to E and G. The measurement directions are also set randomly in the experiment along 4 different directions. And after decoding the atomic signal, you discover, you reveal a single photon number in the cavity. It does not mean that this photon number pre-exists to the measurement. It means that you acquired information about the system and that you learned something about the system. And indeed, the field in this experiment was not an initially flat photon number distribution. It was a coherent field containing on average 3.7 photons. And you see that even ignoring this, if we look at the measurement result, indeed we can reveal this photon number distribution. And here is the average, the histogram of of all the measurement results performed with a lot of repetition of the same experiment, which is preparation of a coherent state, send 100 atoms in the cavity, deduce the photon number, put a dot here, and try again. And you see discrete peak. In between, there is some noise, because sometimes the measurement noise, the shot noise of detecting 100 atoms is not completely negligible, so you have some errors. But you see that if you look at these peaks, you reconstruct very well the coherent state, the Poisson distribution of the coherent state without putting it by hand in the model initially. So that's a very nice measurement apparatus which projects the field in a given realization, which on average reconstruct the photon number distribution. So if you observe carefully, you could see that here there is eventually a discrepancy between the Poisson distribution and the population we find in vacuum. And maybe some of you can give the reason for which this peak is too large. Indeed, it has to be like this. It's related to the fact that in the first experiment, we were measuring the photon number modulo 2 and only the parity. And here, the modulo is not 2, it's modulo 8. And there is, if you extrapolate the Poisson distribution, a small probability to have 8 photons, which is wrapped into 0. So this is not an error. This is consistent with the measurement. So here is a resume of what we did in this single realization of the experiment, where we initially observed the collapse of the field state into a state containing 5 photons. Then we checked that repeated measurement gives the same result if the measurements are close enough so that cavity damping does not yet occur. And that's the signature of quantum non-demolition measurement. The field is still there, and if you measure it again, you find again the same result. Then you observe quantum jumps and the cascade down to the vacuum in the cavity. So that's the point I wanted to focus on today. And now I try to draw some general conclusion about the point of view introduced by von Neumann about this kind of measurement. So von Neumann was claiming that measurement proceeds in 2 states. First, Hamiltonian evolution, then state projection. So in this experiment, these 2 steps are well identified. The atoms, when they fly through the cavity, they are not connected to anything else to the outside world, so they only have Hamiltonian evolution with the cavity field. And then you see that for having a measurement apparatus which behave like the postulates, you have more or less to divide the measurement in this kind of first step when you build correlation between 2 systems by evolution. And evolution means that a measurement is not an abstract thing, it's some interaction between 2 physical systems. And here, as the atom is isolated from the rest of the world, this step is isolated to the next step, which will be the coupling to the real macroscopic world, which occur when we ionize the atom. And indeed, the state projection indeed is not a mysterious evolution. It's just the fact that once you build correlation, if you take one system out and that it interacts, that it does not interact anymore with the system, the mere fact that you acquire information about this system tells you something about what is inside the cavity. And so that's what we observed in this experiment. So the state projection here appeared as just the acquisition of information. And I can do one comment about the acquisition of information, which does not mean that the information pre-exists. Before detecting the atom, before ionizing it, we have an entangled state, so a kind of multi-level EPR pair between the atom and the cavity field, and no way to consider that this is already projected before you ionize the atom, which means that the measurement result is not written anywhere before you finish the measurement. And this was already very clearly pointed out by experiment demonstrating violation of Bell inequality, which really shows that in an entangled state, the measurement result does not pre-exist to the measurement. So we are not just reading out something which is already written, we are extracting information from an entangled state. And if you remember that I started saying that quantum theory is a stochastic theory of measurement result, there is nothing strange than in a stochastic theory, when you get information, the object you use to describe your system probability distribution is changed according to this information. So the point of view I would adopt here is that the state projection postulate is the fastest way to say that when you acquire information, you have to take it into account in order to describe the continuation of the experiment. And indeed, it's the proper way to get the proper correlation between successive measurements. So then back to the Feynman chain. Indeed, we, of course, did not went up to the consciousness of the observer, but we already built, during this experiment, a first version of a Schrödinger cat state by entangling not a single atom, but a collection of 100 atoms with the photon number inside the cavity. So I did not discuss this from the point of view of Schrödinger cat state, and indeed in the next lecture, I will adopt this point of view, not to describe an atomic Schrödinger cat state, but rather a cavity Schrödinger cat state, which is also very interesting in order to understand the second part of the quantum measurement theory, in which I will add the ingredient of explicitly describing the role of the environment to describe the so-called decoherence process. And I thank you for your attention. Okay, we have time for questions. Maybe I was a bit faster than I expected, so questions? Okay.
Hi, thank you for the lecture. I wanted to ask if you are going to talk about, in the part of the coherence, about how you can explain what are the eigenbases in which you measure, how, if you consider the system and the measurement apparatus.
So it means you are anticipating on the next lecture, which will make clear that once you add an ingredient that I did not introduce here, which is dissipation. Dissipation means that the system is open, interacts with the outside world, and indeed, in the entangled state, there will be a basis which will appear as a natural basis for state projection, which is kind of enforced by the environment. So in the case of particle flying in the bubble chamber, the basis was a position basis, basically, as when a particle collides with an atom. It's kind of spatial localization which occurs, and it's dissipative because it finally damps the energy of the particle. And here, considering the atomic cat state, of course, there is some decoherence, but it's difficult to formalize it because it occurs in a complex process, which is the ionization of the atom and the amplification of the information using an electron multiplier. So this is not easily modeled, this kind of environment. And in the next lecture, I will focus on looking at the cavity cat state, where the energy damping has a very simple description in terms of master equation, and where the coherent state basis appears as the natural basis of classical state in relation to that. But it's for the next
Thank
lecture.
You.
Other questions? Yeah.
Thank you again. when you talk about the photon number statistic and you show the graph,
Yeah.
could you explain a little bit more about this kind of mismatch with the zero photon number?
Okay,
No.
this discrepancy. So maybe I was adding some confusion with this, but I think it's nice to wonder when you have some experimental results which deviate from this to know whether it's just normal because it's statistical or if it is physical. And the point is that if you look at the meter is an atom, and you see that if you have not 7 but 8 photons, then the atomic spin will point in the same direction as with n equals 0, which means that this measurement cannot discriminate between 0 and 8 photons, and even between 1 and 9 photons, and so on. And it performs a measurement of the photon number modulo 8. Okay, which means that 8 gives the same result as 0. And this explains that 0 is a bit larger than it should, because you see the Poisson law is not yet at 0 when you have 8 photons. Of course, the same argument applies for 9, but then this decays further, and then the contribution of 9, which is included in 1, is nearly within the statistical noise of the measurement. So here, the error bar is the statistical noise, and you see that this point is off by the amount corresponding to the population of 8 photons.
Thank you.
So, and it means that in this experiment, I put the a priori knowledge that the photon number was not larger than 7, which was an approximation for the coherent state containing like 3.5 photons here, but it's not bad approximation. And indeed, a more sophisticated analysis of this experiment allows to discriminate between 0 and 8. Maybe I have the signal there, I'm not sure, because I have not shown it for a long time. No, it's not here, but I can tell you how it looks like. Indeed, to discriminate between 0 and 8, it's enough to wait. Because if you wait, 0 remains 0, eventually with thermal fluctuation of 0.05 photons. So basically, 0 remains 0, whereas 8 will decay to 7. And so in the quantum jump, if you have 8, you will observe kind of jump between 0 and 7. And then after 7, you will see all the cascade. And so the further evolution of the system will, in the end, tell you that it was not 0, but 8. And indeed, this is a very interesting analysis to deduce the photon number from a long chain of measurement, which eventually ends up in the vacuum. And going back the analysis, you can deduce from going back the quantum jump that the initial photon number was not 7, but you can eventually unwrap several times the photon number and count much higher photon numbers as compared to what we did here. Okay? So, who volunteers for another question? Yeah. Oh.
So about the timeline of the improvement of the quality factor,
Yeah.
Your kind of Moore's law. What were like the kind of improvements and the limitations? Well, the kind of improvements that took you to improving the quality factor? Like, what kind of technical
So the technical
aspects?
improvement, basically from here to here, there was two important points. First, indeed, we had bulk niobium. And then for the first cavity, we did as we did for other more simple cavity. We wanted to be able to monitor the quality of the cavity, so the frequency of the resonance and the width of the resonance by microwave measurement with a network analyzer. And for that, you need to couple efficiently photon in the cavity and out of the cavity to monitor the transmission of the cavity. So for this purpose, there was a very small hole in the mirror, which was supposed to be small enough not to cause diffraction losses. But indeed, this hole was also deforming the sphere, and there was a small region of a few millimeters where the sphere was flatter than it should. And this was a big defect for the microwave, provocating coupling to modes leaking out of the cavity. So the first thing we did is to suppress the coupling hole, which made the experiment more challenging. Because when you machine the cavity, when you adjust the setup, you have never infinite precision over machining, which means that you don't know where is the resonance within hundreds of megahertz. And the resonance, the atomic resonance, has a width of a few 10 kilohertz, which is the vacuum Rabi frequency. So you have to find a needle in a forest. And so we had to develop technique to measure the thickness of the mirror without, and the distance between the mirror without directly measuring the cavity. So there are tricks for that. And even like that, you fall within 5-10 megahertz with respect to the resonance. So then you have to find the resonance by using the atom as detector. And indeed, what you do is you send a microwave from the side of the cavity, because there is no coupling hole, but there is diffraction losses. So you use the residual diffraction losses on the border of the mirror with a big microwave pulse to have a few photons entering the cavity. And then you switch off the source. So the field all around the cavity is just going to zero very fast. But the cavity field is still there for a fraction of a second. And then you send a bunch of atoms, which are very sensitive detector, and you make them just, you use them as absorber. So you put them in ground state and look at the probability to excite this atom. And in this way, if you are patient, you find where is the resonance, and then you use a piezo stack to fine-tune the cavity on resonance. But okay, it's kind of tricky. So that's the first thing, suppression of the coupling hole. And the second thing is to switch from bulk mirror here to copper mirror on which we evaporate a thin layer of niobium. And the bulk mirror had a roughness of several micrometers, so the departure for the ideal sphere. Whereas in this case, the short length scale defect, the roughness, is in the range of 10 nanometers, and the total difference between the ideal surface and the machine one is like 100 micrometers between the center and the border without structure. So it's a very smooth deviation that you cannot see on the losses. And then having this machine for having very clean niobium deposited on copper without changing the roughness was the game changer.
And the distance between the mirrors is like not too precise because wavelength is about millimeter size?
So the distance is like 3 centimeters, and it has to be set properly so that the 9th order mode, we don't use the fundamental mode of the cavity, but the 9th order, it has to be exactly in coincidence with the atomic resonance, which can be tuned a little bit by Stark effect, but not in the range of several megahertz. And so then we change the distance with a resolution of a fraction of a micrometer with the piezo system.
Okay, thank you.
Mm-hmm. Another question? Any question deserve to be asked? Yeah.
Thank you for the lecture. So, can you explain again why did you use a toroidal mirror, not a spherical one?
We use
a toroidal mirror as a surface of the mirror. You say that you used a different surface, not a spherical one for the cavity.
You mean the quality surface of the quality?
Yes.
So we need that. So if you have some roughness, the mirror will create diffusion. And there is a well-known formula to describe the intensity of the scattered light, which is related to the RMS roughness squared divided by the wavelength squared, and you take the exponential of that. And so we put the number at some point, and we find that we need a roughness of 10 nanometer in order to reach quality factor larger than 10 to the 11. So in principle, these mirrors are good enough so that the roughness is not the limit of the quality factor to 4 10 to the 10. But maybe it was not your question.
I was talking about the shape of the mirror.
The shape
itself.
of the
Yes.
mirror. You mean the long,
Yes, exactly.
the large scale. So this is not as critical because basically the mode will adapt to this. So in first approximation, we use a spherical mirror, and the mode is a Gaussian mode. But this is only approximation because here the equivalent of the numerical aperture of this mirror is very large. The diameter is 5 centimeters, and half the distance where the Gaussian beam converges is 1.5 centimeters. So it's clear that the Gaussian beam approximation does not apply to describe the beam all over the mirror. In practice, it's not so bad approximation because with the atom, we can reconstruct the shape of the intensity strength, the field strength across the cavity, and it fits very well with the Gaussian we expect. So then if you imagine that you don't have exactly the right curvature for your Gaussian mode, it gets a little bit deformed, but it does not create significant diffraction losses, provided that the deformation is not large at the scale of the curvature. And the radius of curvature is like 5 centimeters. And so if we have an error over this of 100 micrometer, we don't care. It does not impact the quality factor of the cavity. But indeed, it's very difficult to make a quantitative estimate of this kind of effects because this would correspond to be able to calculate numerically the field distribution in the cavity with an accuracy of 10 to the minus 11 or 12 on the field intensity, which is numerically very challenging. I think some people eventually are nearly at this limit, but we did not have these tools at that time. So we made a rough estimate of diffraction losses on the border of the mirror by making the approximation that the beam is Gaussian and that we truncate the wings. And then to be conservative, we made the mirror a little bit bigger, and it worked. But it's difficult to really estimate what is the final limiting factor for the Q. It may be this geometric factor. It may be the residual conductivity of the niobium layer, which is not measured in another way than looking at the quality factor. Okay. Yeah. Another? Yeah.
Thank you. I was wondering, like, usually when you have like an experiment that you perform with cavity QED, you must like perform it multiple times to extract the relevant statistics to the quantities you want to analyze. So I was wondering if you must repeat the quantum non-demolition process to access information about the cavity statistics each time that you perform the experiment, or you can just perform one quantum non-demolition measure in the end of all times you repeat the experiment.
Conceptually, once the atoms have left the cavity, you can imagine that you store them somewhere in a trap, and provided the Rydberg lifetime is long enough, you have a lot of time to measure them. So in this sense, it's not critical to know at which time you read out the measurement. But you know that as soon as you know about the measurement result, you know at that time what is the proper probability distribution to use to describe your system. But indeed, the critical point, I would say the measurement duration is rather the interaction time with the cavity mode. And once the atom leaves the cavity, you can project just when the atom leaves the cavity, or you can wait and project 1 year later if the atom is living for a long time. In the end, you will get the same correlation function between the atoms. Basically, once you do not interact anymore, you have time, provided you don't lose the information encoded in the atom. Of course, if you are interested in having time resolution, you will make the atom close to each other, and you will look at this as fast as possible. This is important, for example, if you want to use this information for doing something. And in our experiments, we use the information to perform quantum feedback to stabilize the photon number. So here, instead of having some decay, you lock the photon number to a number state, which lasts forever, because every time you think that it disappeared, you add a photon with another atom. So then it makes sense to have time. Maybe I can make another comment related to that, the correlation function, because the kind of correlation function are different from the one which are measured in optics, as introduced this morning. And in optics, you basically measure the field which is leaking out of the cavity, and you measure the G2. Here, there is nothing like this G2 that we measure with the atom. We really measure the photon number. We can have correlation function between photon number, which is not the correlation function of a propagating field, but of a field stored in the cavity. And here you see that when you have 4 photons, the correlation tells you that most probably after some time you have 3, and then 2, and then 1. So the G2 is not anymore the right thing, because we are not detecting a field leaking out of the cavity, and this would add losses to the cavity quality that we do not want to have. Okay.
Thank you.
One more. Okay, so I think we can stop, and anyway, you can ask other questions at any time.